Hello everybody, this is Randall Pike. I'm going to present lecture 1.5 today. So this is going to be a section on dot products and projections in Rm. So previous lecture we extended our ideas of vectors in R2 and R3 to arbitrary dimensions Rn. We'll start off with extending the dot product to these vectors, and then a very important application of the dot product, which would be the projections. Okay, so I'm sorry I've already written out some of these notes. I'm just going over it one more time, so I'll pace myself here. So what we'll learn today is the dot product in Rn, and there's several names for the dot product. Scalar product and inner product are also synonyms for this term, the dot product. So you may see those in the literature. Then we'll talk about projections. Unit vectors will be vectors of norm 1. We'll use those from time to time. The dimension of a space will be the number of components in the vectors that you're studying. So in this case, if there's n components, it'd be n-dimensional space. And we'll talk about a hyperplane, which is a generalization of our notion of a plane in 3 dimensions. Notice the plane in 3 dimensions is a 2-dimensional object, and therefore we talk about hyperplanes as being subspaces in Rn of 1 less dimension. Okay, so we'll talk about those later on. So let's talk about the dot product first of all in Rn. So let me take 2 vectors in Rn. Okay, and I will, so there's their components. So we define the inner product written this way as the product of the components. So V1 times W1 plus V2 times W2, etc. And from that, we define the norm. So the norm squared, which would be the dot product of V with itself, which is the sum of the squares of the components. And therefore, the norm of a vector will be the square root of the sum of the squares. Okay, so that's the same formula we saw in R2 and R3. So for example, here I have 2 vectors in R4, and I can compute their inner product. So let's compute that. So let's take the product of the components. So V dot W will be 1 times 2 plus 0 minus 6. So 2 minus 6 equals minus 4. So that's the dot product of V and W. The norm of V is the sum of the squares of its components. So it'd be the sum of 1 plus 1 plus 4, which is 6, and take the square root to get the norm. So there's my norm of that vector. And similarly, the norm of W would be the square root of the sum of its squares, which is 4, 1, and 9, which is 14. Okay, so I've computed the dot product and the 2 norms. And from this, I can talk about the angle between vectors. So even though I can't sketch these vectors in R4, we'll still talk about the angle between 2 vectors, just as we did in R2 and R3. And we can compute that angle using the dot product. So I'll use this formula here for the dot product, which has this cosine alpha, alpha being the angle between the 2 vectors. Now this formula, which should be compared to the first one I gave you. So there's our definition of the inner product, but this is another formula for it with the cosine, and that was proven, you can prove that using the cosine law, and you can see that in the textbook. So using the second formula for the dot product, which has the angle alpha in it, we can find an expression for the cosine of alpha, and I've done it here for this example. So the cosine of alpha is minus 4 over square root of 6 times square root of 14. Well, that's a negative number here. Cosine alpha is negative, so I know that the angle is greater than 90 degrees. So it kind of looks like this diagram here, if I could sketch it out. So the vectors are slightly pointing away from each other. And if I compute the arc cosine of this number, I'll get 115.8 degrees. So that's what we would call the angle between these 2 vectors in R4. Also, we have the notion of orthogonality. So if the inner product is 0, using that formula with the cosine alpha in it, that means cosine alpha is 0, and that occurs when alpha is pi over 2. And then when that happens, we say the vectors are orthogonal. So that's the same notation, same terminology we had in R2 and R3. Orthogonality referring to the vectors whose angle is 90 degrees, so the dot product is 0. Then we have the triangle inequality, which works in all dimensions too. So there it is here. So the norm of the sum of two vectors is less than or equal to the norms of the two vectors added together. And I can see why this is related to a triangle. I can draw a triangle given the two vectors u and v. Then I draw a third line, u plus v. And from these three vectors, I form a triangle, which I'm drawing down here, just the sides of it. So here's a triangle whose sides have lengths v, w, and u plus v. And the triangle inequality simply says that the length of the side of a triangle is never longer than the sum of the sides lengths of the other two sides. So in this case, we usually isolate the u plus v length, and we see that it's no longer than the sums of u, norm of u, and norm of v. Triangle inequality, useful in many applications. Another useful inequality is the Cauchy-Swartz inequality. And that has to do with an estimate on the size of the absolute value of the dot product. So we can easily prove this inequality once we establish that formula with the cosine alpha in it. So here it is. So writing that formula for the dot product, I get that the norm of the absolute value of u dot v is equal to the absolute value of this expression. And knowing that the norms of vectors are positive, I can rewrite this as norm of u times norm of v times the absolute value of cos alpha. And we all know that the absolute value of cos alpha is less than or equal to 1. And therefore, we get our inequality. So the absolute value of u dot v is no bigger than the product of the norms of the two vectors. And that's another important, useful inequality. Okay, so let's talk about hyperplanes. So first of all, I'm going to recall the method of finding the scalar equation of a plane in R3. So I've made a sketch here. So there's my plane up here. Okay, this piece of paper line there. And I've put a point P on the plane. Okay, so that's what we're given when we're defining a plane. We're given a point P that's on it, and we're also given an orientation. That's the normal vector M. So there it is here. And that specifies a plane geometrically. Remember, a plane is like in 3 dimensions. A plane is a piece of paper that you're holding up in 3 dimensions. And if you want to specify where that plane is, you need 2 pieces of information. One is its orientation, how is it tilted, and also where is it in space. So the orientation we determine by specifying a normal direction. So that's a vector that's normal to the surface, so perpendicular to the surface. Once that's specified, then the orientation of the plane is specified. But where the plane is in space is still left unknown. So you specify one point that's on the plane, I'm calling it P, capital P, and then that fixes the plane in space. Okay, so that's how you define a plane geometrically, perfectly well defined. So there's my plane there, and I've put my normal vector at the point P. You can put it anywhere on the plane, but it's customary to put it there with its base at the point P on the plane. Now notice there's many normal vectors, so any vector parallel to this n would also be a normal vector, would define the same plane. Let's give this n components ABC, and let's give P components P1, P2, P3. Notice I'm borrowing that notation in the textbook. So P is a point in space with coordinates P1, P2, P3, but little p with the arrow, the vector little p, is the vector from the origin to P. Okay, so I've drawn the origin of my coordinate system here, and you can see the line OP vector from O to P. That's the little p you see in the textbook. And similarly, the vector from origin to Q is the vector OQ, which we'll denote by little q, and it has coordinates x1, x2, x3. So our question is the following. Is this point Q in our plane or not? So that's one of the main uses of the scalar equation of a plane. You want to test whether a given point is in the plane or not. Okay, so here's our point that we want to inquire whether it's in the plane or not. This is Q, and we're going to derive conditions on its coordinates that assure that it's in the plane. So its coordinates are x1, x2, x3. Now we see that if it is in the plane, then this vector PQ from P to Q should be perpendicular to n. So that's this condition right here. So that's the condition that Q must satisfy for it to be in the plane, that position vector from P to Q, remember P is in the plane, and if Q is in the plane, then that vector PQ is going to lie in the plane and therefore be orthogonal to M. So n dot PQ will be 0. So let's write this out and see the equation that we obtain. So the vector PQ is the vector Q minus P, and therefore the inner product or the dot product with n can be written this way, and I'll distribute the dot product over that difference between Q and P, and I'll obtain this equation here. On the left-hand side, I have n dot Q, and this is the unknowns, remember, because Q has the coordinates x1, x2, x3, which I want to find conditions on so that it sits in the plane. On the right-hand side, n dot P, this is stuff that I know because I've specified the plane, meaning I've specified the n and I specified the p. So writing down n dot Q, I get this equation right here, ax1 plus bx2 plus cx3 equals some scalar d, which happens to be the dot product of n and p. There it is. So this is our scalar equation for the plane right here, you see? So now when I select a point Q, and I know its coordinates, x1, x2, x3, I can decide whether it's in the plane or not by looking at this equation and seeing whether it's satisfied or not. So in other words, if ax1 plus bx2 plus cx3 is equal to d, it is in the plane. If that sum is not equal to d, it is not in the plane. All right, so that was a brief summary of how we obtained the scalar equation of a plane in R3 based on its geometrical definition of a plane, its orientation and a point on the plane. And one use of this scalar equation to determine whether a point is in the plane or not. In hyperplanes, we follow the same idea. We'll have a direction vector, a normal vector, that's my m here. Okay, and it's a vector in Rn, so it has components m1 to mn. And I'll find a point P that's in the plane, so there it is with coordinates P1 to Pn. And now I take an arbitrary point in Rn, this capital X with coordinates x1 to xn, and I want to know conditions on the coordinates x1 to xn so that it lies in this hyperplane. And once again, the condition will be that the vector between P and X is orthogonal to M. So that's this condition right here. Okay, so you can think about a hyperplane, this vector PQ being in the hyperplane if it's normal to this direction, this direction vector M. So once again, writing out the vector PX in terms of little x and little p, I get this equation. And on the left, if I isolate that, I'll have m dot x is equal to m dot p. Now the m dot x part is the one that contains the coordinates of my vector x, so here it is. And on the right-hand side, I get a scalar d, which is the inner product of m and p. So once again, I get a very similar formula for the scalar equation of a hyperplane. So it's a single linear equation in n variables, and similar as the scalar equation for a plane was in 3 dimensions, is a single linear equation in 3 dimensions. So whenever you have a point in Rn that satisfies this equation, then it is in that hyperplane. Okay, so there's hyperplanes, and we'll see use of them later in the course and also in applications. Areas that use linear algebra will also use the idea of hyperplanes. An orthogonal projection. Okay, so this is an important use of the inner product, of the dot product. All right, so let's take a situation where we have a vector A and a vector X. What we want to do is rewrite the vector X as a sum of 2 vectors, x1 and x2, of certain properties. So the x1 and x2 have certain properties. Here's the formulas for the decomposition that we want. x1, we want to be in the span of A. So it is a scalar multiple of A. And I want to choose the x2 to be perpendicular to A. So that's a very specific criteria on these two vectors x1 and x2. There's only one way you can do this, and it's given by these formulas. So here's my x1, formula for x1, and you can clearly see that it's parallel to the vector A. It's a scalar multiple of A. And x2 is necessarily just x minus x1, and that's simply obtained by taking this equation and solving for x2. So once I've specified x1 and x is known, then x2 is determined by this equation. Namely, it's x1 minus x minus x1, and therefore it's this formula here. Now, we want x2 to be perpendicular to A, so let's check. I'm doing that right here. Let's check x dot A. Okay, so I distribute this dot product over the two vectors I see on the right there. So I get x dot A minus x dot A over A squared times A dot A. But A dot A is A squared. Therefore, I get x dot A minus x dot A. Therefore, I get 0. So this formula up here for x2 does assure us that this vector x2 is orthogonal to the vector A, just as this formula assures us that x1 is parallel to A. And that's the only way you can write x as a sum of vectors with those properties, one parallel to A and one perpendicular to A. There's only one choice, and this is it. Here's some notation that we'll see later on and throughout the course. X1 part of this vector, so that's the one parallel to A, we'll call the projection of we'll call the projection of x along A. So proj, P-R-O-J, is short for projection, and I have to specify what direction I'm projecting onto. That's why the little a is on the bottom, and the brackets hold the vector x that you want to project. Or x2 is the other part, which is perpendicular to A, so that's this term perp, short for perpendicular, with a little a in the subscript to indicate that's the vector it's perpendicular to, and we're taking that part of x here. So that's x2. Okay, so that's the notation, and it's pretty common notation in linear algebra. I'll just add this to the sketch over here. We see that here's my vector A in the sketch, and there's the line through A, the span of A, and there's my vector x. So I'll draw here my vector x2, okay, which is the perpendicular part, and it's pointing that way. And down here I have my projection part, x1, projected onto A. Okay, so if I gave you this picture and I said sketch an x1 and x2 with those two properties, you'd be obliged to make this exact sketch. There's no other way you can choose x1 so that the part x2 is perpendicular. It has to be this exact x1. Okay, so there's a sketch of the two parts of this vector x, one projected along A and one perpendicular to A. Okay, so that's projection onto a vector, or we say it's projection onto A or onto the span of A. It's the same thing. We get the same vector. So orthogonal projection onto a line Rn. Notice the term, we have the term orthogonal here. Just to bring it to your attention, there are projections in linear algebra. We won't talk about them here in this course. But this orthogonal projection, when you see that word orthogonal there, it's referring to this property that one vector is along the subspace and one vector is orthogonal to it. Okay, so we're only, in this course, we'll only talk about these orthogonal projections. So orthogonal projection on a line in Rn is this formula right here we've just described, and the perpendicular part orthogonal to A is going to be x minus that. Notice it's just, you just remove the x1 part from x to get the part that's orthogonal to the vector A. Okay, here's an example then in R4. So I'll take a vector A and a point x, a vector x. So I want to know how I can decompose this vector x into two vectors, one parallel to A and one perpendicular to A. And I use the formulas above. So the part parallel to A, which we denote by projection of x along A, proj A of x, is given by the formula above. So x dot A over A squared times the vector A. And if we do x dot A, we get 3. And the norm of A squared is 21. Multiplying that against A, I get this vector here. All right, so there's my vector parallel to A. And the perpendicular part now is simply removing from X this parallel part. Okay, so I'll do that, and I get this vector down here. Okay, so these two vectors that I've just highlighted, their sum, you can add them up, you will get X. Now, let's just check our answer here. And the reason I do these little checks from time to time, not just for you, but for myself also, is because in linear algebra, although it's a challenging course because it's you know, abstract concepts, many concepts being described and discussed and related amongst themselves, the actual technical calculations are pretty simple. It's just adding, subtracting, multiplying numbers. But you can be doing that many times in a calculation, and so it's prone to algebraic errors, as you will realize in this course. So it's always helpful to stop once in a while and do a check somehow that your calculations are correct. So for here, for instance, I can just check to see whether the perpendicular part I've just computed is in fact orthogonal to A. So I'll simply compute this dot product. So let's do that. Let's do A dot perp x. Okay, so I'm using the perp x I found right here. Okay, now let's compute the dot product with A. So first component, 2 times 5 over 7 gives me 10 over 7. Second component, 1 times 6 over 7. There it is. Third component gives me 0. Fourth component is 4 times minus 4 over 7, which is minus 16 over 7. And indeed, it is 0. So this gives me confidence that, in fact, that is the correct answer, and I didn't make an algebraic error. If it didn't turn out to be 0, I would go back and check my calculations. All right, so now that we have the notion of orthogonal projection, we're going to use a very important property of it, that related to minimum distances and nearest points, and subsequently, more generally, best approximations. So best approximations are going to be a very important application of linear algebra in lots of fields outside of linear algebra. And it's related to orthogonal projection. So I'm going to talk about these concepts, minimum distance, nearest point, in terms of a line in R2, but you can also do the same discussion with planes in R3, and I just make a note here. That's in 1.5 of the text, and I'll do an example like that later on in these notes here. Okay, so here's the situation. I have a line, x vector. So there's a line in direction D. It goes through the point P. All right, so there's my D at the origin. There's my line parallel to it. And there's my point capital P. The vector little p is the vector pointing from the origin to this point capital P. There it is. And I have a point Q that is may or may not be on the line. Okay, so I've drawn it so it's off the line. Our question is, what is the nearest point on the line to Q? Okay, so if I drew the picture here, you would see that the point on the line that is closest to Q would be that point that's just below Q. Okay, so I'm going to draw it now. So there's my R. Now, how do I know it's just below Q, closest to Q? That will occur when the vector, this one right here, let me draw it this way. So this is R to Q. When R to Q is orthogonal to D, then the point R is closest to Q. Okay? And therefore, the distance from Q to R is the norm of that vector. And that's the minimum distance from Q to the line. In other words, from among all the points in that line, which one gives you the minimum distance between the point and Q? And that's this point R I've drawn. And once I've found that point R, the actual value of the distance is the norm of that vector from R to Q or Q to R, either one. Now, this vector RQ is the perpendicular part of the projection of PQ, which I'll draw now. So there's my PQ. So oops, not with that one, but let me draw with this one. So there's my PQ. All right, so there's P to Q. So PQ, the perpendicular part of PQ projected onto D is this RQ vector. Okay, so now remember the quantity I want in this problem to begin with is what is the minimum distance? Okay, and that's the norm of this vector RQ. And now I have a formula for this vector RQ given by the perpendicular part of the vector PQ, okay, perpendicular to D. Okay, so I can find that vector now. Here's some formulas that are useful as a reference. So P to Q, the vector P to Q can be written as the vector P to R, which is along the line, plus R to Q. Now, the vector PR from P to R is the projection of PQ along D, if you look at the picture, okay, where the vector RQ, as I said above, is the perpendicular part. Okay, so this one I've just highlighted here. This is the decomposition of that vector PQ into two pieces, one parallel to D. Okay, so that would be, maybe I'll draw it in here now. That would be this one here. Okay, so there's that vector. This is my projection along D of PQ. Okay, it's there. And the vector RQ is the perpendicular part. So it's the part that's perpendicular to D. So those two vectors together give me PQ, as you can see. I can also write this this way, from Q to P, the vectors going the other direction. I just reverse all my vectors, and I'll get another formula for QP this way, which may be useful sometimes to have it that way. So either one works. Now, we've found a formula for the minimum distance. There it is right here. Okay, so there's my minimum distance. It is the norm of that vector right here. Okay, now you can compute that vector because you know P and you know Q, and you use the formula above to compute perp of PQ along D. Okay, so you'd first find the projection of PQ along D, and then you'd subtract that from the vector PQ. You would get that vector perp PQ, and then you would compute its norm, and that would be the minimum distance. But what is the point R? Okay, so that's actually the question I started off here. What is the point R? So let's look at our picture here and write down some formulas, and that will give us a point along the line that is closest to Q. Okay, so I see from the picture here that OR, okay, so from origin to R, can be written as O to Q plus Q to R. Okay, so O to R is equal to O to Q and then Q to R, which is OQ plus perp along D of Q to P. Okay, not P to Q. Okay, so this is a formula right here. Oops. This is a formula right here that gives us the coordinates of R. Remember, the coordinates of the vector OR is the coordinates of the point R. And on the left, that's what I want. But on the right, I have everything that I need. I know I have the point Q, so I have the vector OQ. I know its coordinates. And I know the vector P, so I know the coordinates of the vector QP, and then I can compute the perpendicular part of it, and then I can get my vector OR. So I want to make, so this is done in the textbook. They do an example like that exactly. Example in the text. So they compute the point on the line. Okay, that is closest to a point Q here. Okay. Now, I'm going to do an example that extends this, a bunch of exercises. I'm going to do this problem here. Okay, so this is a similar problem. Problem D I'm going to do, okay? You're given a plane, and you're given a point, okay? So this is similar situation as up here. Given a line, given a point Q, okay? So now the plane here, I'm given the algebraic, or the scalar equation of the plane. You could be given the vector equation of the plane, okay? That the method of solution would be different. Here I'm going to work with the scalar equation, and you'll see why that makes it a little bit easier to do. And I want to find the closest point to this Q. So I've made a little sketch here of what this might look like. So there's my plane up there. There's a normal to it. I put it at the point P. P is in the plane. Q is some point here. Looks like it's off the plane. There's my vector from P to Q. Now, I'm going to sketch in here what this point R may look like, the closest point in the plane. So once again, I try to imagine myself in this plane, and I'm looking, or at the point Q, and I'm looking down at the plane, and right below me is the point R that's closest to it. Okay, now what do I mean by right below me? Well, I mean that this is 90 degrees right here. Okay, so the vector from R to Q is parallel to N. Okay, is parallel to N. So the this distance here, this vector right here, sorry, I don't need to write that. I'm just going to write R to Q. This vector is the projection of the vector PQ along N. Okay, so there's my PQ, there's my projection, and therefore the PR, you can see, is the part that's perpendicular. It's the perp part of this projection on N. Okay, so I've made the sketch of those two, and therefore minimum distance, that doesn't look right, minimum distance from Q to plane is a norm of a certain vector. So here I'm going to write it as RQ or QR, it doesn't matter, which is the norm of that projection of PQ along N. That's the minimum distance. Okay, now how do I find the point R? Okay, actually we can do this right now. Let's work through this. Example. So I've given you the coordinates here. So if I can find the projection along N of PQ, then I will have the minimum distance, and then we'll go and find the actual point. Okay, so there's less work to do to find the minimum distance, just like up here. If I wanted the minimum distance from Q to the line, I can compute that by computing the norm of this perpendicular projection PQ onto D, the perpendicular part, and I'd be done. But to find the actual point R, see, that's this one down here, I need to go a bit further. I need to find, I need to compute these two vectors right here, okay, the actual vectors, add them up, then I will have the point, okay. Similarly down here, I can first compute the minimum distance by computing that vector and then taking its norm. And then I'll find a way to find the actual point on the plane. So let's do the minimum distance first. Okay, so I want the projection then. Okay, so projection of PQ along N. Okay, that's that vector up here, and that will give me the minimum distance. So let's compute that. So according to our formula, it's going to be N dot PQ divided by norm of N squared times N, okay, which is, okay, so the norm N dot PQ, sorry, did I do this? P and Q, yeah. So let me write this out up here. So PQ, I need the coordinates of that vector here. So I have my P, I need a P, right? So I didn't compute a P. So I need to find a P, a point on the plane. So my point is 1, 1, 1. Okay, 1, 1, 1. Okay, so this point is on the plane because when I plug in 1, 1, 1 into that equation, I get 4. So there's a point on the plane. So notice I needed to do that step here. Sorry, I needed to do that step to compute this projection because I didn't, it wasn't obvious. I mean, I wasn't given a point on the plane, but I can easily select one by trial and error, just by guessing. So there's 1, 1, 1. It is a point on the plane. I'm going to use that point on the plane to do these calculations. Okay, and therefore, I should fill it in here. My P to Q has coordinates 0, 1, 2. Okay, so there's my vector PQ now. Okay, so now I can compute these quantities. So N dot P is going to be, I'm going to write down my N up here as a reference. Okay, so my N is 3 minus 1, 2. Okay, so then when I compute that dot product, I'll get minus 1 plus 4, so I'll get 3. And then the norm of that vector N squared is 14. And then multiplying that by my N, 3 minus 1, 2. Okay, so that's my vector, my projection vector of PQ. Okay, so the norm of that then, so the minimum distance is the norm of this vector. Okay, so 9 over 14 minus 3 over 14, 6 over 14. Okay, so I'll compute the norm of that vector. That would be the minimum distance. Okay, now let's find the point on the line, the point R now. So I want to know where, sorry, on the plane. So where on the plane is this point R that has that distance from Q? Well, let's look at the picture now. So I see the vector OR from origin to R can be written as O to Q. Okay, so O to Q plus or minus, okay, let me do it two ways, projection onto N of PQ. Okay, so that's the vector pointing from Q to R. Okay, so this will be O to Q plus Q to R, Q to R. Okay. Good. Now I've just finished computing the projection of P to Q. So let's do the calculation. So it's equal to, so O to Q, here's my Q, good. So I'm going to write, just to simplify things, I'm going to write it as, well, I'll just write it out here and you guys can check my algebra. So there's my OQ, 1, 2, 3, minus the projection I just computed, 3 over 14, 3 minus 1, 2. Okay. And I get 1 over 14, 5, 31, 36, written without a scalar. I'll write it as 5 over 14, 31 over 14, and 36 over 14. Okay. Now, once again, you know, because of the numerous algebraic steps we've had to do here, I want to check this answer. So check. In other words, is R on the plane? Is this R I finally computed on the plane? Okay, so you just want to plug in these numbers here, okay, into the equation of the plane, which is, I'll rewrite it here in black, 3x minus y plus 2z equals 4. Okay, and you can check that indeed it is. Okay, yes. Okay, so when you plug in those numbers, 5 over 14 for x, 31 over 14 for y, and 36 over 14 for z, you do get 4. Okay, so that gives me confidence that I've found the right point. So this problem, we've answered 2 questions. We found the minimum distance from Q to the plane, and we found the actual point in the plane. Okay. So notice the what I want to put at the bottom here is the minimum distance. Okay. So for lines, okay, so summary, just a bit of a summary. Sorry. All right. Min distance to line, okay, and that uses this is the projection going back to here. Okay, so it's the perpendicular part. Okay, the perpendicular part. So it's perp d pq. Okay, where p and q are defined in those sketches, and the minimum distance to a plane, which we've just finished here, was the norm of this vector, which was projection of n pq. Okay, now these are the 2 formulas that I've used here, and you'll see in the textbook. Now I want you to look closely at those, okay, and it'll help you understand what's going on here. So when we're talking about a line, okay, we have the d, the direction of the line. When we're talking about a plane, we have the orientation vector, the normal n. Now look at, for the line, so both of these problems, minimum distance, require orthogonal projection, okay, onto those distinguished directions, the d or the n. Okay, so they both require orthogonal projection, but they use a different component of it. For the line, the vector you're taking the norm of is the perpendicular part of this vector pq. Okay, whereas for the plane, you're taking the projection along the n. Okay, you see that? And if you follow these examples and look at these pictures, you can see why they're different. So the formulas are different fundamentally because here for the line, notice the direction vector. See, it's along the line, whereas down here, the direction vector, the n, is not along the plane, it's perpendicular. Okay, so this is the origin of why one problem uses the perpendicular part and one problem uses the projection part. So once again, well, not once again, but once here, I emphasize that it's not a good idea just to try to remember formula. It really helps to understand where they come from, because here you could have made the mistake that because the minimum distance to the line uses the perp d formula, then the minimum distance to the plane uses the perp n formula, and that in fact is incorrect. And if you didn't realize that, you'd run into problems and you wouldn't know what was happening. So it's much better to, in this situation here, if I were you, I would make these little sketches like this one here and this one up here, just to see what's going on. And that's, once you understand those sketches, then you're set to go. You understand the situation, you've understood how these different vectors are created from those various points and how you utilize the distinguished directions D and N in these problems to find minimum distances. Okay, so there's a minimum distance, and then I should add in the summary here, and find the closest point. Okay. So you can do the minimum distance without finding the closest point, but often you do want to find the closest point, okay? But we know how to find the closest point, don't we? Okay, so I'm done with that for this lecture. And I will see you next time for the next lecture, 1.6.